All right, good morning, mathematicians. Before I get into today's lesson, I just wanted to say that I'm sorry that I am out again today. I really do miss you guys, and I don't like being away from you guys. So I just want to let you know that I will be back soon. And I thank you guys for being patient, and I thank you guys for hanging in there. So just one more day, okay? All right. So I'm going to walk you through lesson 2.1, and this is going to be on page 22, and we're going to go through 2.2 as well. It's a little longer, but you guys can do it. You guys can make it through, okay? All right. So our focus question for 2.1 is, how can you decide when finding common multiples is useful in solving a problem? So you'll notice in this lesson that we're going to focus a lot on multiples. We talked about multiples for a little bit in a previous lesson, but this lesson is going to focus on it completely, okay? So we have some vocabulary here. Common multiple, which is a multiple that two or more numbers share. So if we take a look at the numbers 2 and 3, let's go ahead and write the first 5 multiples for these numbers. So for 2, it's 2, 4, 6, 8, 10. Okay, and then for 3's, it's 3, 6, 9, 12, and 15. Okay, now we have to ask ourselves, well, what multiples do these two numbers have in common? And you'll notice that they both have a 6 in common. So that's what we call a common multiple. It's a multiple that they share, that these two numbers share. Okay, and now I'm going to talk about the main part of this lesson, where we are trying to find the least common multiple. Okay, now the definition says that the least common multiple is the least common multiple that two or more numbers share. Okay, you guys already know what a common multiple is, right? It's a multiple that numbers share together. Okay, but now we're going to add the word least to it. And if you guys want, you guys can write this word. Least also means the smallest. Okay, so we're looking for the smallest number that is a multiple of two or more numbers. Okay, so let's take a look at some examples. I'm going to try and find the least common multiple of 4 and 5. Let's go ahead and list the first 5 multiples of 4. It's going to be 4, 8, 12, 16, and 20. And then I'll do the same for 5. 5, 10, 15, 20, 25. Okay, now remember, we're finding the smallest common multiple that these two numbers have. Okay, so when we write our lists, it'll be the number that shows up first, or it'll be the number that both numbers have that show up first. And in this case, it's going to be 20. And we abbreviate least common multiple as LCM, so you're going to tell me that the LCM is equal to 20. So 20 is the smallest multiple, or the least common multiple. Okay. All right. So with that, we're going to go ahead and we're going to answer some problems all regarding least common multiples. Okay. So if we read this problem, it says the large Ferris wheel makes 1 revolution in 60 seconds. The small Ferris wheel makes 1 revolution in 20 seconds. How many seconds will pass before both Ferris wheels are both at the bottom? Okay, so bear with me here. We have a Ferris wheel. Okay, so you start at the bottom here, right? You get onto the ride. Then when they say 1 revolution, right, they're talking about, well, how long does it take you to go all the way around and end up at the bottom again. Okay, so we'll say that this is one revolution. How long does it take you to go around the Ferris wheel? All the way around. Okay? So, they tell us that the large Ferris wheel makes one revolution in 60 seconds. Okay? So, starting at the bottom, we go all the way around. That's going to be 60 seconds. That's how long it's going to take. Now, let's think about, well, how long is it going to take for it to go another revolution, a second revolution? Right? You might be saying, well, hey, look, it's gonna revolve, or it's gonna do another revolution in 120 seconds. Right? Let's do two more. Another revolution is going to be at 180 seconds, and then one more revolution is going to be at 240 seconds. Now I want you guys to label these. Okay, so 60 seconds represents one revolution, one time around the Ferris wheel. 120 seconds is 2 revolutions. 180 seconds is 3 revolutions. And then 240 seconds is 4 revolutions. We're going to use that information later because there's going to be a question where it asks you how many revolutions does each Ferris wheel make. Okay, so we'll use that information a little later. Now let's take a look at the small Ferris wheel. They say that the small Ferris wheel makes one revolution in 20 seconds. Okay, so we're gonna list the multiples here. So 20 seconds represents one revolution. That's how long the small Ferris wheel takes to go from the bottom all the way around the Ferris wheel and back to the starting point. Okay, so if the small Ferris wheel were to go around another revolution, it'd be at 40 seconds, and then 60 seconds. Now, can we stop now that we have a common multiple? Yeah. Yes, you can, right? Because we're looking for this thing called the least common multiple. So when you're working these problems, the first number that these two things share is going to be your least common multiple. So you'll notice that, hey, the large Ferris wheel has 60 and the small Ferris wheel has 60. And that's the first number that we see that they share. Okay? Now, before we answer this, I want you guys to label how many revolutions did the small Ferris wheel do. So 20 seconds is 1 revolution, 40 seconds is 2 revolutions, and then 60 seconds is 3 revolutions. Okay? Now the question asks how many seconds will pass before both Ferris wheels are both at the bottom again. So we said that both Ferris wheels will be at the bottom at 60 seconds. Okay, I also want us to write, you guys, how many revolutions did it take to get to this least common multiple? So the large Ferris wheel, remember, take a look at what 60 is. Well, 60 we said is 1 revolution. So the large Ferris wheel only revolved once. There's only 1 revolution here. Whereas the small Ferris wheel, how many revolutions did it take to get to 60 seconds? Well, this one revolved around 3 times, so there were 3 revolutions. Okay, let's go ahead and do it again. So we have more Ferris wheels. We have a large one. We have a smaller one. Okay, and our job is to find out, well, how many seconds will pass before both Ferris wheels are both at the bottom again. Okay, so it's a very similar process here. We're going to take this information for the large Ferris wheel, so it makes 1 revolution in 50 seconds. So we're going to start listing the multiples of 50 here. And I might do the first 5 multiples, right? So 50, 100, 150, 200, 250. Okay, now let's start listing the multiples of, or for the small Ferris wheel, which is 30 seconds. So we have 30, 60, 90, 120, 150. As soon as you guys see a common multiple, you're going to stop. The common multiple here is 150. So if we think about how are we going to answer this, it says how many seconds will pass? Well, we're going to say 150 seconds will pass before both Ferris wheels are at the bottom again. So we'll say that. Okay, now I want you guys to count the revolutions. How many revolutions did the large Ferris wheel make? How many revolutions did the small Ferris wheel make? Okay, so 50 seconds is 1 revolution, 100 seconds is 2, and then 150 is 3. So it looks like the large Ferris wheel did 3 revolutions. Okay, let's take a look at the small. How many revolutions did it take to get to 150? Well, that's 1, 2, 3, 4, and then 5 revolutions. So 5 times around the Ferris wheel in order to get to 150 seconds. Okay, so here is where I'm going to have you guys try this on your own. Okay, we have one more Ferris wheel problem. So they tell you that the large Ferris wheel makes 1 revolution in 20 seconds. The small Ferris wheel makes 1 revolution in 11 seconds. How many seconds will pass before both Ferris wheels are both at the bottom again? Okay, so you guys are going to do a very similar process here. Start writing the multiples for the large Ferris wheel. Start writing the multiples for the small Ferris wheel. I can guarantee you guys that there is a least common multiple for this problem. Okay, so if you don't find one, keep going. Keep writing multiples until you find one in common. Okay, this one should take you maybe like 3 to 4 minutes. Okay, so pause the video now. Work with your partners. Again, 3 to 4 minutes. Okay. Okay, you guys, hopefully you paused the video. Take a look here. How was it? You'll notice that it probably took you a little while. You had to list quite a few multiples before you were able to find that least common one. Okay, so the large Ferris wheel, it took us 11 revolutions. We had to find 11 multiples of this number in order to get the least common one. Whereas if we looked at the small one, right, the small one revolved every 11 seconds. And we had to do 20 revolutions. We had to do 20 different multiples, okay? So, that being said, we're going to keep going with these multiples. We have another set of problems here, okay? Oh, sorry, I'm getting ahead of myself. Question D, it says, for questions A through C, find the number of times each Ferris wheel goes around before they are both at the bottom again. Remember when I had you guys write how many revolutions each Ferris wheel made? Ah, there we go. You already did it. You already answered question D, so we can leave it blank. Awesome. Okay, let's keep going. I'm on page 23. Okay, so it says, our focus question says, how can you find the least common multiple of 2 or more numbers? Okay, so we have one vocab word today, and they're called relatively prime numbers. Okay, and this is a pair of numbers with no common factors except for for the number 1. Okay, so I'll give you the first example here. So there is the number, let's do 2 and 3. Okay, when you try and find, or when you look at the factors of 2 and 3, what do they have in common, right? I know the factors of 2 are 1 and 2, and I know the factors of 3 are 1 and 3. The only thing that these two things have in common is the factor of 1, which is exactly what we're looking for. So these are relatively prime numbers, okay? They're kind of like relatives in your family, right? They're closely related because they do have this one thing in common, okay? Another example, let's go with some larger numbers. Let's do 29 and maybe 31. The factors of 29 are 1 and 29. The factors of 31 are 1 and 31. Again, the only thing that they have in common is that factor of 1. Okay, if I were there, I would ask you, what do you guys notice about the two numbers that we are trying to compare? And hopefully you guys notice that the numbers or the pairs that we're creating are prime numbers, right? So prime numbers are technically relatively prime numbers, okay? All right, so we have some more problems here. Not as many, but we have some problems here that all involve multiple scan, okay? So, except this time we're working with these things called cicadas, okay? So question A says, suppose 13 and 3-year cicadas both appear this year. When will both types of cicadas next appear together? Okay, now if you have no clue what a cicada is, they're these little buggies. Look, it's so cute. Look at those eyes. There's also this one, yeah, but they're kind of related to grasshoppers, maybe crickets, right? Cicadas kind of make those like buzzy sounds that you hear. Like if you guys are going hiking, you might hear bugs going like bzzz. No, that's not the greatest. That sounds like a bee, but you know what I'm saying. There's this kind of a crickety sound that's kind of loud. It sounds like I don't know what it sounds like, okay? But Google it, YouTube it, okay? Then you'll hear what I'm talking about, okay? All right. So I actually, yeah, so we're going to do question A together. Then you guys are going to do question B. And then we'll do question C together, okay? Because question C is a little bit more in depth. All right, so doing the same thing here. We have the 13-year cicadas, right? So they appear once every 13 years. So we're going to write the first, no, let's start with the first 5. That's usually a good place to start, okay? So we have 13, we have 26, we have 39, then we have 52, and then we have after that is 65. Yep, okay. All right, and next let's do the 3-year cicadas. Okay, and we're going to list all the multiples of 3 until we get something in common with 13. Okay, so 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Yep, we're still going. I'm going to drag my list. I'm going to make my list go under here. 33, 36. Have anything in common yet? Nope. Oh, wait a second. There we go. 39s. So the question is asking us, when will both types of cicadas next appear together? So we'll say both types of cicadas will appear in 39 years. That's quite a while. Okay, and well, why does this work? Why is 39 such an important number? Well, if we remember, this is the smallest number, or the smallest multiple that is shared between 3 and 13. Well, what do we call the smallest multiple? We call it the least common multiple, right? So the reason why is, well, 39 is the least common multiple. And I want you guys to write that out. Least common multiple. Especially for right now. So 39 is the least common multiple, and that's why, that's your explanation here. Okay? All right. So we're at question B. Okay, and this one I want you guys to do on your own. The only difference here, I'm going to read this first, and then you guys are going to pause the video and then try this on your own, okay? So let's read the question. It says, suppose there are 2-year, 4-year, and 6-year cicadas that all appear this year. After how many years will all 3 types of cicadas appear together again? So this time, instead of just 2 different types, we have 3 different types of cicadas we're looking at, okay? So you're going to start out by writing your multiples. I usually start with the biggest one first because that one kind of gives us a picture of what numbers might be in common. Okay, then we can go to 4, and then lastly we can go to 2. Okay, so list the common multiples, answer your question just like we did here, answer your question in words, and then make sure you guys include the explanation. Okay, those are all important. So do the math, show me the numbers, then write in words, explain. Okay? Okay, hopefully you guys pause the video and let's take a look at this. So we listed the multiples for 6, and then that's a good starting place, starting with a larger number, okay, and then maybe doing the first 4 or 5 multiples. Okay, then we went to 4, and then I went to 2, and then we kept going until we had a common multiple in all 3 numbers. Okay, and our conclusion was that all 3 cicadas will appear in 12 years. This is the least common multiple, or the LCM, of 2, 4, and 6. So 12 is the least common multiple of 2, 4, and 6. Okay, now you're probably starting to wonder, Mr. RG, is there a shortcut to do this? I'm getting tired of listing all of these multiples and then finding what's in common. And I'm going to say, yes, there is a shortcut, and we're going to get to it, I promise. Okay? Our friend Stefan here in question C actually proposes an idea that we could possibly use. Okay? So, it says that Stefan developed a method to determine the next 2 types of cicadas, the next time 2 types of cicadas will appear together. He says that if you multiply the cycles together, you get the next time that both types will appear together. And we're going to have to answer this question. Well, does Stephen's method work for any pair of cycles? If so, explain why. If not, provide an example for which Stephen's method does not work. Okay? So we're kind of being like lawyers here. We got to make some arguments. Either you're for his method or you're against his method, and you have to prove it. Okay? So we're going to test a few examples here. Okay? So I'm just going to draw from this page. Let's take a look at 13 and 3. So we're going to test, so let's test the 13 and 3-year cicadas. So remember, Stefan, I'm going to alternate between both of them, argues that if you multiply the cycles together, you get the next time that both types will appear together. Okay? We already know the least common multiple for 13 and 3. We know the LCM of 13 and 3 is 39, right? With the work that we already did, we already discovered that the LCM is 39. So what Stephen is proposing is that if we multiply the cycles, if we multiply these numbers here we should get the least common multiple. So let's ask ourselves, does 13 times 3 equal 39? Yes, it does. Okay, so Stephen's method works here. Now let's take a look at another example. We're going to test, let's test 6 and 4. The least common multiple for 6 and 4 the least common multiple of 6 and 4 in question B, we said was 12. Right? We know this for a fact already. Now, we're going to test Stephen's method here. We're going to multiply 6 and 4. So does 6 times 4 equal 12? No, it does not. No, it doesn't. Okay. So now can we answer this question? Does Stephen's method work for any pair of cycles? Or any pair of numbers? Or all pairs of numbers? We say no, Stephen's method does not work for any pair. Or I'll say for all pairs of numbers. But I must say, I like how Stephen is thinking. You know, he's trying to think of a shortcut. He's trying to think of a pattern that works to help him solve this problem. Okay, and that's what we're going to take a look at now. So if you stay with me, right? Oh, wait, hold on. Yeah, actually, this is, so page 24, as we're scrolling past here, this is your homework. So the summary, you can assume comes from page 22 and 23. Okay, so that's where your summary should come from. Okay, let's keep going. Now here, we're going to combine some of the things that we've talked about already. Okay, and this is lesson 2.1 and 2.2. It's still within the same realm, but now we're talking about that shortcut. We're talking about that strategy that we can use to find the least common multiple of two or more numbers. Okay, so it says, how do you use prime factorization to find the least common multiple of two or more numbers? And yes, you saw it. Yes, you're probably screaming. Yes, we are using prime factorization to our advantage here. Okay, this method allows us to see what the least common multiple is. Okay, so in this box here on the left, we have the process for how to find the least common multiple using prime factorization. But I thought of another way that we could think about this. Okay, so first, let's say you want to make a new friend. Okay, and usually when you're making a new friend, one of the first things that people do is they talk about things that the two people have in common, right? Like, oh, hey, I noticed that you have My Hero Academia stickers on your Hydro Flask. I love My Hero Academia. Or, I noticed that you bring your sketchbook to school all the time. Look at my drawing markers that I have. Look at all the colors that I have. Right? You try to find something that you have in common with that new person. Okay? So we're going to tell a story about some numbers here. So I'm going to do number 14 up here. Let's say that 18, we're going to look at 18 and 21. They want to become friends. Okay? Now, the second step we're going to do is we're going to look for what they have in common. So I'm going to write that down. And yes, you should be writing this down. Look for what they have in common. And this is when we're going to use prime factorization here. Okay, that's going to help us find out, well, what do they really have in common? So we're going to do our factor trees, or as one of my other kids said, factor mountains. Okay, so prime factorizing 18, 2 is the smallest prime number. And then I know that 2 times 9 is 18. 9 is a composite number, so I need to break that down more. And the smallest prime number that goes into 9 is 3. And then, of course, 3 times 3 is 9. So now we have the prime factorization of 2 times 3 times 3. I'm going to leave it in this expanded form here. I'm not going to use exponents just yet because you'll see. Okay, so next, let's do the same thing for 21. Smallest prime number that goes in. Well, 21's not even, so 2 doesn't go in. Let's try 3. Oh, yes, well, 3 does go in. There we go. So 3 goes in, and then 3 times what is 21? Oh, wait, 7. So the prime factorization for 21 is 3 times 7. Okay, now remember, we're looking for what they have in common. Well, you'll notice that 18 has a 3, and 21 has a 3. Okay, so I'm going to write at the very bottom here, we're going to take what's common between both of them. So 3 is definitely going to be involved here. Okay, now once you guys, when you're making new friends and you've talked about what you have in common and you guys are starting to hit it off, then what makes friendship awesome is that you guys are also very unique, right? There are things that are different about the two of you, right? And 18 and 21, they do have some different things about them. Now we're going to take a look at what is unique about the numbers. And what makes us unique is what makes our relationships interesting. Imagine if everyone was the same. Could you imagine how bored we would get? Yeah, we would get really bored. So being unique is very important to our relationships. So we're going to take a look at what is unique about the numbers. So what is unique about 18? What does 18 have that 21 doesn't? Well, you'll notice that it has this 2 times 3. So what I'm going to do is I'm going to take that and add it here. Well, not add it, I'm multiplying, okay? But I'm inserting this 2 times 3 into the problem here, okay? Now, let's find what's unique about 21. Well, what's different about 21 is that it has this 7 here. So I'm going to take that, and I'm going to add it here. Sorry, not add, I'm going to multiply it here, but I'm going to insert 7 into this problem, okay? So now what we're going to do is we're going to take what's unique and what's common, and we're going to multiply everything together. So I'm going to do 2 times 3 times 3 times 7. So 2 times 3 is 6, 6 times 3 is 18, and then 18 times 7 is 126. And there you go. You have the least common multiple for these two numbers. So let's go ahead and write that here. LCM is equal to 126. Okay, we're going to practice this because this is a little bit, I know this is new, so it looks really complicated, okay? But the more you practice it, the better it's going to become, the more you're going to get used to it, okay? All right. So 15 and 21, let's go ahead and work on that. So 15 and 21 are trying to become friends. Let's look for what they have in common. Let's prime factorize both of these numbers first. So 15, what is the least, or what is the smallest prime number that goes into 15? Well, 15's odd, so I know 2 doesn't work. 3, does 3 work? Yes, it does. So this is 3, and then 3 times 5 gives me 15. Okay, we already did the prime factorization of 21, which is up here, so we can actually just take that. So the prime factorization of 21 is 3 times 7. Let's write this down here, 3 times 5. Now remember, now that we've prime factorized both of them, let's look for what they have in common. I'm going to highlight them. So I see that they both have a 3. So when I calculate my LCM, which I'll write down here, I know that 3 is going to be involved. So I take what they have in common, and I'm going to be multiplying some numbers together. Next, let's find out what they have that is unique. Okay, what is something 15 has that 21 doesn't? Well, 15 has this 5. So I'm going to bring it down, insert into my problem here, and I'm going to multiply it. Okay, and then don't forget about what's unique about 21. Remember, both numbers are unique. Both parties are unique here. They will have something that someone else doesn't. So we're going to bring it down. We're going to multiply it. So our least common multiple is going to be whatever 5 times 3 times 7 equals. Okay, so I know that 5 times 3 is 15. If I multiply 15 times 7, that's 5 times 7 is 35. 7 times 1 is 7, plus 3 is 105. So the LCM here is 105. And there we go. Okay, so treat these problems like the numbers are trying to become friends. Okay, that might make a little bit more sense than what it's listed here in the box. But if the box makes more sense to you, then that's fine too. You can use that as well. But you guys will need to learn how to use prime factorization to help you find the least common multiple. Okay, there will be problems on a quiz or a test that say use prime factorization to find the least common multiple, and you have to do this process. Okay, so yes, you will have to learn it. Okay, so here's what I want you guys to do. I want you guys to try 16 and 17 with your partners. Okay, maybe try it on your own first, and then once you're done, then look over at your partner and say, hey, are you finished yet? Let's compare answers. And if they are finished, then yeah, compare answers. If not, maybe help them out. If they're stuck, help them out. Okay, so all right, mathematicians, take a look. Take a look at 16 and 17. Okay, so some things you guys may have noticed in number 16 especially is that this, here, let me use blue here. Okay, the numbers had 18 and 24 had a lot more in common than the problems with 15 and 14. Okay, so it doesn't matter how many numbers that they have in common, you have to include all of them. Okay, so notice how I highlighted 2 times 3 because both 18 and 24 had a 2 times 3. So I brought it down into my calculations. Okay, then of course you find out what's unique, then you bring it down and you multiply from both numbers to get 72. Okay, and then number 17, we already had the prime factorizations for 21 and 24, so I just borrowed that information from myself to save me some time. Okay, I found out what they had in common, which was those highlighted 3s, and then I found what was unique about both, and then I multiplied all of those things together, and it looks like their friendship is going to last for 168 years. Okay, let's work through number 18 together, the last problem we're going to do today. And of course, it's a word problem because word problems are probably, word problems have the highest chance of relating the math that we're learning in school to the real world. Although it doesn't always sound like that, right? Like, when would you buy 70 watermelons? Yeah, typically in a math class, yes, you would. But that's why I said word problems have the highest chance of relating to the real world, because some of them, maybe they don't. Okay, but this one probably does. At a store, hot dogs come in packages of 8, and hot dog buns come in packages of 12. what is the least number of packages of each type that you can buy and have no hot dogs or buns left over? Okay. Now, if I were in class, I would ask you guys, what do you think this problem is trying to have you do? Okay? Because trying to make sense of what the question is asking you guys is the most important step you guys need to figure out. Okay? But because I'm not there, we can't have this conversation. But it usually helps to underline what the question is asking you. Okay? But this is quite a long question, right? What is the least number of packages of each type that you can buy and have no hot dogs or buns left over? Well, if we ask ourselves and we kind of relate this back to what we've been learning so far, you'll probably start to imagine that this question is asking us to find the least common multiple, or the LCM, of the numbers 8 and 12. And that's what we're trying to do here. When we find the LCM of 8 and 12, when we find the least common multiple of 8 and 12, we are finding the least number of packages of hot dogs and hot dog buns that we can buy, so that way we have no hot dogs or buns left over. Okay, so we're going to do the same thing we did above. We're going to do the prime factorization of both, right? We got to find out, what do these two numbers have in common, because they want to be friends. Okay, so 8 is an even number, so I know that the smallest prime number is 2, and then 2 times 4 gives me 8. 4 is composite, so we need to break it down even further. 2 is the smallest number that goes into 4, that is prime, and then I know that 2 times 2 is 4. So the prime factorization of 8 is 2 times 2 times 2. Let's do the same thing for 12. 12 is even, so automatically your brain should say the smallest prime number that goes into 12 is 2. Now 2 times 6 gives me 12. 6 is composite. 6 is also even, so again, it is a factor of 2. And then 2 times 3 gives me 6. So we have 2 times 2 times 3. Okay, now let's highlight what they have in common. I see that 8 has 2 2's, and so does 12. So when we calculate the LCM, we're going to take those 2 2's, so I'll highlight what they had in common there. Okay, and now let's take what's unique about 8. Well, 8 has an extra 2 there, so we're going to bring it down and multiply. And then what's unique about 12? Well, 12 has this 3 here, so we're going to take that, we're going to bring it down, and we're going to multiply. Now I have everything that I need to find my least common multiple. 2 times 2 times 2 times 3. Well, 2 times 2 is 4, 4 times 2 is 8, 8 times 3 gives me 24. And there we go. But the number 24 I don't think is a good enough answer. We have to make this answer better. So going back to the question we underlined, what is the least number of packages of each type that you can buy and have no hot dogs or buns left over? Right, you guys are learning your race answering, your race acronym is what we call it. Okay, so restate the question, answer it, right? That would be a good time to use that. So 24, well, we have to remember that 24 is the number of packages we can buy. So you can buy 24 packages of hot dogs and buns so you don't have any leftovers. And this is what you would box. That is your answer there. Okay. And the reason why we're writing words is because you guys need to give the number some meaning, right? 24 by itself doesn't really have much meaning. But if you put words around the numbers, then it gives it meaning. That's important. Okay? All right, you guys. So there you have it. That was That was all about the least common multiple, okay? So I gave you a way to start out, how to find the least common multiple, but as you noticed, right, especially for like this one, for question C, that took quite a long time, right? So this method may not always be the best to do, right? It's very time consuming. So that's why we went over how to use prime factorization here. How do we use this to our advantage? Okay, so I'm giving you options here, but you do have to learn how to use your prime factorization, okay? So page 26 is also going to be part of your homework. So we're going to summarize our learning from pages 25. Yeah, just from page 25 here, okay? And then you guys have some word problems to do, okay? All right, you guys. If you're still confused, send me a message. I will be at RAM today, okay? So if you'd like to work through some of these problems, we can go over it during RAM, okay? All right, you guys, hang in there, and I promise I will be back soon.